object, it will involve a single action, like an apple falling from the tree. This will probably happen one time, after which the apple will remain at rest. But some motion is periodic, meaning repeated, like the motion of the pendulum on a grandfather clock or the vibration of a spring. We will refer to this kind of motion as simple harmonic motion.
Simple harmonic motion is a type of periodic motion where the restoring force is proportional to the displacement of the body from the equilibrium position. This restoring force acts in a direction opposite that of the displacement.
Say, we have a spring that is attached to some stationary surface, and on the other end of the spring, there is a block of a particularly mass. If we pull this block so as to expand the spring and we release the block, it will vibrate back and forth between more compressed and less compressed states.
If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or less compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest.
If we were to graph it, will display sinusoidal behavior, just like a trigonometric scene function, where the block continues to occupy the same position over a period of time, which is why we call this periodic motion. X is equals to 0 at the equilibrium position of the block where it was before, hold it and assuming zero friction. The block will oscillate between positive x and negative x indefinitely.
In equation, F equals negative dx, where F is the restoring force or spin force, x is the displacement of equilibrium position, and E is a proportionality constant. The negative sign simply means that the restoring force and displacement are oppositely directed.
The direct proportionality between the restoring force and displacement distinguishes simple harmonic motion from other types of vibratory motion. Systems exhibiting simple harmonic motion are called simple harmonic oscillators.
The simplest form of a simple harmonic oscillator is a body of mass m oscillating on one end of an elastic spring, also known as the mass spring system. And this figure right here shows that at equilibrium position, the spring offers no restoring force. If the spring is stretched, the displacement is positive and the restoring force is negative.
If the C spring is compressed, the displacement is negative, but the restoring force is positive. Note that the mass of the spring is negligible to the amount of stretching or compressing force.
Guys, can you give us some example problem?
A spring has a spring constant of 65.5 Newton per meter and it is stretched with a force of 15.3 Newton. How far will it stretch? So the formula that will be used is F equals negative kx. To solve the problem, first let's identify the given. So we have F, or force, is equals to negative 15.3 Newton. Note that it became negative because it acts in the opposite direction to the displacement. Then we have K, or the constant, which is equals to 65.5 Newton per meter. So, X is what we are looking for.
After identifying the given, let's write the formula to be used, which is F equals negative K times X. Then, let's substitute the given values. We have negative 15.3 newtons equals negative 65.5 newtons per meter times X. Then, let's divide both sides by 65.5 newton per meter. Cancel 65.5 newtons. The answer is 0.234 meter. So the string stretches 0.234 meter. I hope you learned a lot in this video. Thank you for watching. Bye!